All right, let's dive right into this explainer and uncover the secret engineering behind literally the most common building material on Earth. I mean, when you look at a towering skyscraper or a massive bridge, what do you see? Most of us just see concrete, right? But what is concrete really? Today, we're cracking open the surface to look inside.
Now, cement gets all the glory, and honestly, people mistakenly use it as a synonym for concrete all the time. But today, we're focusing on the crucial, invisible skeleton that actually holds our modern world together. Because cement, that's just the paste. The true heroes here are the aggregates.
Here's our agenda for today. We'll start with the foundation of concrete, move on to classifying aggregate pipes, and then look at the importance of grading. After that, we'll calculate the fineness modulus, check out aggregate moisture states, and finish up with the alkali-silica reaction.
Section 1. The foundation of concrete. What exactly is an aggregate?
By definition, an aggregate is simply an inert material mixed with a binding material, like cement or lime, to prepare mortar or concrete. Think of the aggregate as the hard, unyielding skeleton of your concrete, while the cement paste is really just the muscle and glue holding those bones together. It's the aggregate that actually provides the sheer structural mass and handles all those crushing compressive forces. And because this skeleton is made of heavy stuff like rock, sand, gravel, and crushed stone, it gives normal weight concrete an unbelievably high density. We're talking anywhere from 2,200 to 2,400 kilograms per cubic meter. To put that into perspective, that sheer, massive weight is entirely thanks to the aggregate packed inside the mix.
Moving on to Section 2, classifying aggregate types, from minerals to rocks and sand.
So not all bones in this skeleton are made of the exact same stuff. Depending on the chemical minerals present, aggregates are actually sourced from all three major rock types on Earth. You've got concrete skeletons built from igneous rocks like volcanic basalt and granite, sedimentary rocks like sandstone and claystone, and even metamorphic rocks like marble and slate. And the base minerals, whether we're talking silica, silicates, carbonates, or sulfate, totally dictate the properties of the aggregate. Oh, and fun fact, this is also why engineers categorize sand by its source, like pit sand, river sand, or sea sand. The origin drastically changes its chemical makeup and even the sharpness of the grains.
Practically speaking, we split these aggregates into two broad categories using a very strict size cutoff, 4.76 millimeters. On one side, you have fine aggregate. This is mostly sand, crushed stone, or stone screenings that fall below that 4.76 millimeter mark. And this fine stuff usually makes up about 35 to 45% of the total aggregate mass. On the other side, coarse aggregate. This contains your larger gravels, pebbles, crushed stones, and brick qua. While they typically range from 3/16 of an inch up to 2 inches, engineers have to carefully calculate the maximum size of aggregate for any specific project. Why? Because those stones absolutely must be small enough to pass smoothly through the steel rebar reinforcements without getting jammed up.
Now, even within that fine category, precision is everything. The ASTM classifies sand strictly by its size. For instance, fine sand, which is smaller than a 1/16 inch sieve, is used for plaster. Moderate coarse sand is used for mortar. But specifically, coarse sand, which falls under the number 4 sieve size, is what's required as the fine aggregate in concrete to ensure real structural integrity. You absolutely cannot just scoop up beach sand and expect a skyscraper to stay standing.
Section 3. The importance of grading. Building the 3D puzzle. But you can't just toss coarse rocks and fine sand into a mixer randomly. You have to perfectly engineer the mix, and this process is called grading. Essentially, grading is the particle size distribution of an aggregate, and we figure it out using a sieve analysis, literally passing the material through wire mesh with square openings. By physically separating the aggregate into precise piles of different sizes, engineers make sure the mix falls within strict grading limits. Staying inside these limits is absolutely crucial for the concrete's workability, achieving maximum density, and honestly, making sure you don't waste money on extra cement.
Here's the core idea. You have to treat the aggregate like a massive 3D puzzle. The golden rule is that the smaller particles will fill up the empty pores in between the larger particles. So every tiny void left by a large crushed rock must be perfectly filled by a smaller piece of gravel. And then, the tiny voids left by that gravel, those get filled by coarse sand. Getting this void gradation right minimizes the empty space, which in turn minimizes the amount of that expensive cement paste needed to glue the whole shebang together.
Section 4. Calculating fineness modulus. Measuring the mix.
So how do we actually measure if our 3D puzzle is going to fit together properly? Engineers use a really clever mathematical index called the fineness modulus, or FM. By passing a sample through progressively smaller wire mesh sieves, starting from a 9.5mm opening all the way down to a microscopic 150 micrometers, they weigh the fractions retained at each stage to get a cumulative profile. In this example, adding up the retained masses gives us a total of 1100. By dividing this cumulative percentage by 100, we calculate an exact numerical value, the fineness modulus. This number basically gives us the average size of the particles in the mix, guaranteeing our puzzle is perfectly balanced.
Section 5. Aggregate moisture states. Water and the skeleton.
Okay, so once the grading and size distribution are theoretically perfect, we have to introduce a highly variable real-world element, water. When we think about rocks and gravel, we usually picture them as completely solid and impermeable, right? But they aren't. They have microscopic pores, meaning they act kind of like hard sponges that absorb moisture from their environment.
Because of this, aggregate can exist in 4 highly distinct moisture conditions. First, it can be oven dry with absolutely zero moisture. Second, it can be air dry, meaning it's absorbed some water, but less than its full potential. Third, it can be saturated surface dry, where its internal pores are totally full, but the outside surface is dry. Or fourth, it can be completely damp or wet, carrying excess water on the outside. Now, if builders miscalculate this, say they assume the aggregate is dry when it's actually damp, it introduces hidden water into the mix. Even worse, surface moisture actually causes fine aggregates to push apart and expand in volume. This is a super deceptive phenomenon known as the bulking of sand. If you don't account for bulking, it completely alters your critical water-to-cement ratio and can fatally compromise the entire concrete skeleton.
Section 6. The alkali-silica reaction, the hidden disease.
And that brings us to the absolute highest stakes of all, a microscopic disease that can literally bring down massive, carefully engineered structures. Sometimes the real danger isn't physical force, it's chemical. The alkali-silica reaction, or ASR for short, happens when the active mineral constituents of our carefully chosen aggregate rocks chemically react with the alkali hydroxides, like sodium, potassium, and calcium, that are found right there in the concrete itself. Essentially, the bones start reacting with the glue. This wicked reaction forms a gel that expands tremendously when it absorbs moisture, basically swelling the concrete from the inside out.
This internal swelling is a slow-moving disaster, and the scary part is you can't see it happening inside the structure until it's way too late. On the outside, it presents visually as a distinct network of deep mapping cracks, heavily closed or spalled joints where the concrete is literally just popping right off, and severe relative displacements as structural elements are literally pushed out of alignment by that immense internal pressure.
Just look at these terrifying examples. They perfectly illustrate the grim reality of ASR. On the left, you're seeing a massive bridge support pillar totally covered in a severe network of cracks. On the right, a close-up showing just how deep and pervasive these fissures really are. And remember, this damage isn't from an earthquake or a physical impact. This is how a failure at the microscopic mineral level literally tears apart the heavy concrete infrastructure holding up our cities, piece by agonizing piece.
We've journeyed from the exact sizes of sand grains needed to build a concrete skeleton all the way to the microscopic chemical battles that can tear it down. So here's a question for you. Knowing what you know now, how many concrete structures around you right this second are quietly suffering from these invisible reactions? The next time you walk past a massive building or drive over a bridge and spot a cracked concrete wall, you'll know that the true failure might not be age or weight at all. It might just be a hidden, silent battle between the alkalis and the carefully graded aggregate skeleton holding the city itself together. It definitely makes you look at the sidewalk a bit differently, doesn't it?